All right, now I want to prove this theorem, theorem 108. And this is definitely an interesting one. I want to go through the proof because, unlike 107, the techniques here are very useful for the rest of the course. Specifically, the way in which the induction is carried out. So, let's go ahead and assume the hypotheses, and then we'll try to prove f equals g. So assume that, and then let me copy and paste a bunch of stuff. All right. Assume that f and g map n to x. So they are sequences taking values in x, and assume these 3 bullet points. And we have one teeny tiny little goal here: prove f equals g. So f and g are 2 functions. So how do you think we will prove that they are equal? Your first instinct, at least early in the course, is to prove f is a subset of g and g is a subset of f, which is a good instinct. But hopefully that has since been updated because these are functions. If you have 2 functions and you want to prove they're equal, then there's this more natural feeling, more elegant way of doing it, I guess, which is just show that their domains match and show that their outputs are the same for any given possible input. So we have these 2 things to show: domains match and outputs are the same. By the way, how do I know they're functions? I know they're functions because I'm writing this mapping notation, right? This mapping notation always says 3 things about each of the things involved. So it says about f that f is a function, n is its domain, and x contains the range. G is a function, n is the domain of g, and x contains the range of g. So that's how I know they're functions. Okay, so let's prove that the domains are equal and that the outputs are equal for any given input. Okay, well, there's nothing to prove regarding domain. They both have domain n. So let's just point that out. How about better to start a sentence with a word rather than a symbol? We have domain f equals n equals domain g. So let's line up our goal. So by theorem 53, we only need to prove that f of x equals g of x for all x in the domain, which is n. So by theorem 53, we only need to prove, or it remains to prove, it remains only to prove that f of x, I could use x, here we use x because we were in kind of an x mood when we wrote this, but maybe we should use n here. It doesn't really matter, since it's a bound variable, as you're about to see. F of n equals g of n for all, here's the quantifier that's binding it, for all n in the natural numbers. Okay, so how am I going to do this? I'm trying to prove that a certain thing is true for all n. So earlier in the course, your instinct might be, well, I'm trying to prove a for all n statement. So how about a universal generalization type argument? I'll say consider any natural number n, and then for that natural number n, try to prove this, while leaving n arbitrary. That's a good instinct, but again, hopefully that's been updated. Now, when you want to prove that something is true for all natural numbers n, you should always consider that induction might be a better way to do it. And in this case, it definitely is, considering the nature of the information we have about these functions. We have sort of information about, how f of next of n is related to f of n. This is just screaming induction, right, in order to prove anything about f of n. All right, so we will prove, let's make it clear what we're going to prove by induction. So we will prove by induction that well, this exact thing that I said, that for all n, but I want to write it down like this. Now, this is exactly the format for something you prove by induction, right? You're proving a property of natural numbers. So for all n, if n is a natural number, then, and then something about n. So if I look down here at the statement of mathematical induction, the theorem that I'm going to use, this is the format of my conclusion, my desired conclusion. This is what the theorem lets me conclude at the end. And yeah, I have something for all n, if n is a natural number, then blah. And what's playing the role of phi when I apply this theorem? What's my phi? It's f of x equals g of x, right? Where the x is whatever is getting replaced in different places here. So I know immediately how to structure this. Base case, induction step, and let me fill in what I have to prove. Well, for the base case, we must prove that f of 0 equals g of 0. And then, okay, I was going to go and also fill in the induction step and then come back and fill in the proofs for both of them. But the base case is done so quickly, let's just get it out of the way. One of our assumptions, literally, is that f of 0 and g of 0 are both s, and therefore they are equal. I think our assumption should really look more like, not that it makes a huge difference, but probably our assumption should look like this, since it's all about f of 0 and g of 0, f and g both having s as a starting point. That's what it's all about. Anyway, we have this by assumption. So base case done. Now for the induction step, I need to prove, I get to assume, so suppose n is a natural number, and so that suppose n is a natural number, that's because this is the induction, this is what I'm proving for the induction step, and I get to suppose n is a natural number. Then I'm trying to prove this. So, and assume now the induction hypothesis, this. So assume f of n equals g of n. Then we must prove that f of next n equals g of next n. Right? That's this statement, but with the n's replaced by next n. So this is what we must prove. Okay, well, luckily, our assumption tells us exactly things about the situation we're in here. We have a natural number n, and so universal instantiation. For our particular n, we have f of next n equals r of f of n. G of next n equals r of g of n. So our goal is this. Let me put that in yellow. That's our goal in yellow. And here's what we have. We have by assumption that f satisfies the recursion rule. So f of next n is r of f of n. Right? And then g also satisfies the recursion rule. So g of next n is g of r of n. I'm sorry, that doesn't make any sense. R of g of n. And do you think these are equal? And if so, why? Can you point to what makes them equal? It's this, right? It's the induction hypothesis. So this equal sign is the induction hypothesis. If f of n equals g of n, of course, r of f of n equals r of g of n. That's not using any fancy properties of r in any way. That's just using sort of axiom 2, or rather theorem 4, that if f of n and g of n are equal, then any expression that has an f of n, you can replace the f of n by g of n and you get something equal. Any term. Well, that's it. That completes the induction step, and therefore it completes the proof. So now we know that we have uniqueness. So how come uniqueness was needed? How come existence alone wasn't sufficient? Like, Why isn't theorem 107 enough? If you have theorem 107, then that tells you that there exists a function, given a starting point and a recursion rule, there exists something that has that starting point and satisfies that recursion rule. Why wouldn't that be enough? Couldn't we then use existential instantiation and just instantiate a function that has whatever starting point and recursion rule we want? Well, sort of. If you're in the middle of a proof and you need to make an argument about something, then you can instantiate one of these. But instantiation doesn't amount to an actual definition of something. This is a subtle point that we were discussing back here on page 60 in the notes, where if all you know is that there is a green thing, then yeah, you can use EI to get a green thing in an argument. But it's always hypothetical. It's not an actual specific green thing. You haven't defined one. All you've done is sort of brought one into your proof so that you can argue for something else. So how do you define a green thing? How do you define not just a green thing? How do you define the green thing in the context where you know that there is a unique green thing? So if you know there's a green thing and that any other green thing is equal to your original one that you have focused on, how would you then make a definition where you say this is the green thing? Well, we have a language for it. We say let G denote the unique green thing. The unique green thing. This is a sort of informal way of writing what we've formulated as this sort of occupant thing. So we are trying to do the same thing here. If you have a particular starting point, so let's say you're trying to define this sort of sequence, 2, 4, 6, 8, etc., then what you can now do is you can say let F be a sequence of natural numbers, and let it be the unique sequence or function, whatever you want to call it, satisfying f of 0 equals 2 and the recursion rule that f of next n always equals r of f of n. You could write the actual recursion rule next of f of n in this case, or you could just call it a certain function r, where r so typically r is from x to x, where x is where our sequence is taking values. In this case, our sequence is taking values in the set of natural numbers, so it's going to be n to n, is given by r of n equals next of n for all n. So this is what we are now enabling. With theorem 107 and 108, we can say let f be the unique thing having the starting point we want and the recursion rule we want. And again, it is crucial that we have this as a way of making making actual definitions, because we want to define addition coming up soon in the next video, and that's just going to require using recursion as our tool for definition.